Hey everyone, welcome to a brand new video of the Studium. This is the first of many videos. Today we'll be looking over NMR Spectroscopy or nuclear magnetic resonance. This is not a be-all end-all video for NMR. This video is going to be in parts. This is part 1. This video aims to just give you the basic foundation you need to get on to the more complex stuff or the more examinable stuff before you get all confused. So hopefully this video will prevent the confusion and lay down the foundation so that you can build your knowledge step by step. But for now, here are the basics of NMR spectroscopy. Hey everyone, welcome to this brand new video of the Studium. Today we'll be looking over NMR spectroscopy or nuclear magnetic resonance. Now, what this video aims to do is to give you a basic conceptual understanding of NMR. It's not a be-all end-all video. There's going to be a part 2 to this which goes into the specific details of how NMR works and what you will actually do in exam situations. But for now, this video aims to give you a basic conceptual understanding, more sort of the foundation you need to move on to more complicated stuff. Now, what I'll be doing is presenting you the concepts and showing you how it is manipulated in NMR spectroscopy. Okay, so let's get started. Now, before I move on, hopefully you know what spectroscopy is. Hopefully you have a kind of familiarity with all this stuff. But basically, if you don't know, spectroscopy is basically a bunch of techniques that we use to analyze the structure of compounds, to determine the structure of compounds. Now, let's move on to our first slide, which is the basic facts. So, basic facts are that atoms with an odd number of nucleons, that is an odd number of protons and neutrons, they possess this quantum characteristic known as nuclear spin. Now, do you really need to know what nuclear spin is? Not really, but what you do need to know is that nuclear spin allows the atom to create a magnetic field, which can then interact with an external magnetic field. So let's say we have two atoms right here, right? And they possess a certain nuclear spin, a certain direction of nuclear spin. Depending on the nuclear spin, this atom will either produce a magnetic field in one direction or produce a magnetic field in the other direction. This becomes important later on because when we apply an external magnetic field, the atom's magnetic field will align with or against the external magnetic field. So let's try and figure out what that actually means. So we have here an external magnetic field, right? And we have two atoms here which each possess a nuclear spin. Now, what you need to know is that these atoms can actually get aligned with the magnetic field. So let's say for this atom here that when we apply the magnetic field, the magnetic field of the atom actually aligns with the external magnetic field. So you can see here the direction is basically the same. But some atoms can align against the magnetic field, have their magnetic field different. So we call this states, right? Specific states. So if the atom's magnetic field aligns with the external magnetic field, it is in the alpha state. Similarly, if the atom's magnetic field is against the magnetic field, going against the direction of the external magnetic field, it is in the beta state. Now, what you need to know is that beta state and alpha state, they're actually energy differences. So let's go here. Okay, now, so we know that we've learned from the previous slide that atoms can either exist in the alpha state, which aligns where its magnetic field aligns with the external magnetic field, or it can exist in the beta state, which is against the external magnetic field. Now, the cool thing about this is that when we apply this certain radio wave, a certain radio wave with a certain frequency, the atom can actually become excited to the beta state, which essentially means that the atom can actually sort of, align against the magnetic field. So let's actually draw on here to make more sense. Right? Okay, so we've applied a certain amount of energy which allows the atom to become excited to a newer energy state. It has absorbed this radio wave this radio wave with a certain frequency, and it has now jumped or become excited to a higher energy state, which is the beta state, which is aligning against the magnetic field. Now, obviously, it can't stay excited the whole time, right? It has to sort of, it's like when you give sugar to a kid, the kid will become excited for a while, but they're going to tire down soon enough. So what actually happens here is that the atom will move back to the alpha state. Atom will move back to the, the atom will move back to the alpha state and align again with the magnetic field. External magnetic field. Hopefully this is making sense. So it aligns back to the magnetic field. Now the cool thing here is that the atom actually releases that same amount of energy as a radio wave. This is basically the essence of NMR. In NMR, we apply this external magnetic field to the sample, where it can go from a lower energy state, which is the alpha state, to a higher energy state, which is a beta state. And what can actually happen is that as it releases energy, as it moves back to the alpha state, the NMR machine can sort of detect this release of energy, or this radio wave. Now, obviously, I sort of go through the terms here. The change in energy refers to change in energy, refers to the energy difference between the alpha and beta state. The alpha state is where most atoms reside in, as it has lower energy and is just more stable. Okay, so this change in energy, right? This sort of the difference between the alpha state and the beta state depends on the chemical environment of the atom. Now, what do we actually mean by that? We mean by what actually surrounds the atom. So the cool thing about atoms are that they consist of protons, neutrons, and electrons. The cool thing about electrons are that electrons also possess a nuclear spin. What does that mean? It can create a magnetic field that can align against the external magnetic field that we applied. It can almost shield the atom from the external magnetic field, so the atom won't receive as much. Okay, so let's move on. So we know now that from here, we know that electrons possess this sort of nuclear spin, and this nuclear spin can actually shield the atom or the proton from receiving the magnetic field. What does that really mean? It means that it won't have the change in energy. The atom won't receive as much of the magnetic field. The change in energy is lower, and it results in a smaller chemical shift. Now, hold on to the thought of chemical shift. We'll come back to that later. But what it basically means is that it sort of measures the relative magnetic strength and allows us to compare compounds. This will become much clearer later on in the video. So let's say we have this ordinary atom, right? When we apply a magnetic field, that atom will have a smaller energy difference due to the fact that it's shielded by the electrons. So let's say, once we pulse radio waves into it, the atom is going to move up. As you can see, I love using colors because colors are a very good visual way of differentiating the information. So the atoms will move to the beta state. It will flip. Just pretend that, the colors are the same. It will flip to a higher energy state, then release back to the alpha state again, and it will basically retain. Just do this. It will basically sort of release this energy, and this energy will be detected by the nuclear magnetic resonance machine. So, due to the electron shielding of the atoms won't, it won't receive much of the magnetic field. Therefore, the change in energy, this energy state right here, the change in energy is lower than what we had before. What actually happens, I'm going to pose this question. What would happen if the atom is right next to an electronegative atom? What would actually happen then? Well, the change in energy would be much, much more larger. Why? Well, let's actually see this OH. Let's think about, change the color. Now let's actually see what actually happens. So we have this OH here, and we are examining this hydrogen bond. We're trying to determine we're trying to capture the amount of energy it releases when it relaxes back to the alpha state. Due to this oxygen, which is an electronegative atom, the hydrogen won't receive shielding as much. Why? Because if we go closer into it, right? If we try and examine the electron dot structure, we know that we have electrons here, and the hydrogen shares an electron with oxygen. However, if we zoom in closely, these electrons sort of edge closer more to the oxygen rather than the hydrogen. Why? Oxygen has a much higher electronegativity than atom. So electronegativity basically means that the oxygen has a higher ability, attracts electrons more to its side than the hydrogen. So what that basically means is that the electrons won't shield the hydrogen as much as before. We know here, right, the atoms are not next in this situation. In situation number one, the atoms are not next to electronegative atoms, which means that the atom itself will be shielded by the electrons surrounding it. However, for here, right, we know that since because of this electronegative atom, that the electronegative atom will sort of get these hydrogens get these electrons more towards its side, which means the hydrogen won't receive shielding as much, leading it to be more exposed to the magnetic field, which results in a larger energy difference, a larger chemical shift. So since the atom doesn't have as much electron shielding, right, it's gonna have a higher energy difference because of the magnetic field. It's more exposed, it's more open to the magnetic field, and so basically its energy difference will be higher. So it requires more energy. It requires much more energy to flip to the higher energy state. Makes sense, right? And so once it sort of moves back to this alpha state, once it relaxes back to the alpha state, I'll just copy this electron here. So once it moves back to the alpha state and goes back to becoming aligned with the external magnetic field, it will release a much larger energy because it will release a much larger energy as it relaxes back to the alpha state, because it has absorbed much more energy, right? So this much larger energy release would be detected by the nuclear magnetic resonance machine, whatever you want to call it. Hopefully that makes much more sense. So let's look at this thing here. Let's look at this ethanol, the structure of ethanol. Now, I have to explain I want to explain here about two different types of nuclear magnetic resonance techniques. So the most common atoms we try and examine in NMR is H1, swap to another color, it will be H1, NMR, and carbon 13, that's a weird carbon, will be carbon 13 NMR. Now, what do you really, I'll go into more the differences between these two techniques bit in the next video, but what you need to know is that, we can either examine the carbon atom, or we can examine the hydrogen atom at this stage. So what we're going to do here, we're going to examine the carbons here. So first, let's examine the chemical environment. So we have two chemical environments in this atom. We have this chemical environment right here, CH3. I'm going to write that down, CH3. And then we have this chemical environment here, CH2. Now, since this CH3 is next to a CH2, the CH2 is not electronegative, right? So what that basically means is that the carbon will be shielded by electrons. The electrons won't move away. However, since this CH2 is next to this oxygen right here, the oxygen will sort of grab the electrons more towards its side, leading for the CH2 not to be shielded as much by the atom. Right? So this CH3 right here will have a lower chemical shift, while this CH2 will have a much higher chemical shift due to this oxygen pulling those electrons away and not shielding the CH2 as much from the external magnetic field. Now, we measure chemical shift. Chemical shift is a weird concept. We'll explore about chemical shift in much more detail in the next video. But what you basically need to know is that zero basically indicates full electron shielding. The electrons shield all of the atom. It's kind of weird the way I'm explaining it, but hopefully it makes sense more in the next video. Basically, this 0 point is when the electrons fully shield the atom. So as we move away from 0, we sort of get more chemical shift, which means there'll be less electron shielding. So I'm just approximating here, but the CH3 here, this CH3 will have a much lower chemical shift than this CH2, which will have like a much larger chemical shift because of this electron shielding concept. Now, if you move back to the reference sheet, right, let's examine the same compound and we see this reference sheet. You get given this in the exam, this sort of values. We see here that carbon-carbon bond, this carbon-carbon bond is 5 to 40, right? So has a chemical shift of 5 to 40. So it will probably reside somewhere here. But if you can see here, the switch colors, the CO right here, the CO, the carbon oxygen bond has a chemical shift of 50 to 90. So what does that mean? That will mean that it will be all the way here somewhere, this sort of range, this 50 to 90 range. Now, and obviously, why is that? As we explored earlier, it's because of this electronegative atom. It's because of this oxygen that pulls away some of the electrons. So this carbon doesn't get as much electron shielding, so it's more exposed. The CH2 group is much more exposed to the magnetic field, and so it will have a much higher energy difference, which means it will release much more energy, leading to a larger chemical shift. Okay, hopefully that helps. You might need to watch the video again once or twice. I'm going to admit it, I have skipped a number of details, but I'm doing that so that you guys know the sort of the foundation. You guys sort of have the foundation so you can, build up your knowledge and sort of go into more complexity without becoming confused. The next video is going to go more specifically into differences between carbon-13 and proton or H1 NMR. We're going to look more into what chemical shift actually means, TMS, and the main thing in the next video is we're going to look at graphs. We're going to look at how to read proton, carbon-13 graphs and H1 proton NMR graphs, and we're going to see how we actually can use that in exam situations. I haven't mentioned it here, but the next video will look more into the science stuff. I have skipped a number of details, and we're going to go look back into those details once more in the next video, such as, why must radio waves be applied? Why can't radio waves be applied to get that atom to be excited to the beta state? Like that kind of stuff. More explaining of how it actually works. A more complex video on how it actually works. Okay, hope you found that video useful. If you have any feedback for this video, if you think I made any simplifications throughout the video or any mistakes, just let me know down in the comments below so I can make a better, more revised video. Please give us a like if you did find this video useful. Make sure to subscribe and check out the Studium for more resources. We got essay marking, chemistry and physics step study marking, and a whole lot more. And it's all marked by high achievers, so you'll get the best feedback possible. So so subscribe, comment down below what parts of the video you liked, what parts could be better, and your general feedback. And like the video and stay tuned for the next one.